Welcome to a video on NMR. So in this question, we've been given an NMR spectrum of a compound which has the formula C6H12O6, and no, it's not glucose, and we have to deduce the structure of the compound. So what we're going to do is we're going to break this down into a couple of steps. First of all, as you can see, there are 5 different peaks. Each of these peaks represents a different hydrogen environment. What we want to do is work out how much hydrogens there are in each peak. We've been given the ratios, however, we need to work out exactly how many hydrogens each ratio represents. First of all, we're going to add them together. So if you add them all together, you should get 4.8. Remember, there are 12 hydrogens in this particular molecule. So we need to work out how much each peak represents. So 0.8 divided by 4.8 times 12 is equal to 2. And 1.2 divided by 0.8 times 12 equals 3. Okay, so now that we've done that, let's now write down what the splitting patterns are for each environment. Working from the right towards the left, we can see that there are 3 peaks, so it's a triplet. Then we have 4 peaks, so that makes it a quartet. Then again 3 peaks, so it's a triplet. Then you have 1 peak, a singlet, followed by another one with 3 peaks, so it's a triplet. Okay, so now we're going to actually start drawing the molecule. What helps is if you start drawing from the ends of the molecule and work your way towards the middle. Now we know that at the end of a molecule, most of the time you have 3 hydrogens. And as you can see here, we have 2 environments which both have 3 hydrogens. So which one should we start with? I'm going to start with this one because I know more information about it. The fact that it's a triplet tells me there are stuff next to it, which makes it easier for me to draw. Okay, so I'm going to start off by drawing the 3 hydrogens. The fact that it's a triplet means that there are 2 hydrogens next door on the adjacent carbon. And there we go. So just from that 1 peak and 2 pieces of information, I was able to draw this. Now we've identified a new environment which has 2 hydrogens. So which one of these could it be? Is it the 2 with a triplet or is it a 2 with a quartet? Well, the one that we've drawn has already got 3 hydrogens next door. This means that it will have to be at least a quartet, if not higher, in case there are hydrogens on the left side. But we know it definitely cannot be a triplet. That means we've drawn this environment. Okay, so now moving on, let's see if we can use the fact that it's a quartet and its shift to work out what kind of environment this is. So we said that it's a quartet, which means that there are 3 hydrogens next door. There's already 3 there, meaning that there can't be any more on the other side. There are no hydrogens on the left-hand side. So we've already got 3 on the right. That means there are no more on the other side. So we're going to use our hydrogen NMR datasheet to then be able to work out what is going to be on the other side. So the shift is around 2.5 ppm, and bear in mind that there are 2 oxygens in this molecule. So we can see that it must be this environment. Therefore, there's going to be a carbon with a double bond O next door. So far we've managed to draw 2 environments and our molecule has been half completed. Moving on. Now I'm going to draw from the other end. So again, I've got an environment with 3 hydrogens and it's a singlet, meaning next door there's going to be no hydrogen environments. If we look at its shift, it's around 3.2. So again, we're going to look at the datasheet to see if we can figure out what kind of environment it is. Using the datasheet, we figure out that the hydrogen is touching a carbon that is touching an O. So that means it should look something like this. Okay, so now we have 2 environments left to draw. They both have 2 hydrogens and they are also both triplets. So we can pick any one to start with. I'm going to start with the one on the left. The shift is around 3.6 ppm. Again, that means these hydrogens must be touching a carbon which is directly touching an O. So therefore it must be on the other side of this O. Also, the fact that it's a triplet means that there must be 2 hydrogens next door. Just like that. So the new environment that we've drawn must be the last peak. Let's double check if everything matches. So first of all, it's a triplet, which is perfect because in the molecule, it also is a triplet. There are 2 hydrogens on the left. And if we look at its shift, 2.6 matches perfectly with the datasheet because on its right, we have a carbon with a double bond O, and that is representative of something that is at 2.6. So we can see that the carbon double bond O is the reason that it's a 2.6 shift. So we've managed to draw the molecule and we've identified every environment and all the peaks and shifts match. Now some of you might find this a bit confusing because you haven't ever seen a carbon touching an O touching a carbon. I mean, it is present in an ester, but of course in an ester you also have a carbon double bond O as well. This is an ether bond. Now you don't have to name an ether, but you do need to be aware that it does exist. Hey guys, if that video helped you, support our channel by liking, subscribing and sharing it with your friends. And more importantly, if you still have questions, drop a post on our forum at ExamQA.com, where I will personally be there to help answer your questions. Mohammed signing out.